Tonight's lithograph, at the request of our speaker, are Jovian planets. Jupiter, Saturn, Uranus, and Neptune. And she will be telling you about planets. If you didn't get one on the way in, please pick one up on the way out. Although we have such a big crowd here, I might have to go find more. I think I took all we had, but thank you all for coming out in June. Maybe it's just because we have air conditioning, right? Okay, so you're here just for the air conditioning. The astronomy, that's secondary. All right. But the astronomy is not secondary. It's going to be amazing tonight. Probing worlds beyond our solar system with Nikole Lewis. Coming up next month, we have that famous astronomer TBD. He has spoken here many times before, which basically is the reminder that, first of all, July is a very tough month to get astronomers to commit to because they all have all these summer plans. So I have a couple fish in the water that I'm trying to catch and hook for next month. And if I don't get somebody, you'll be stuck with me. I'll give the talk myself. But those of you who know, I tend to give pretty enthusiastic talks, so I'll find something great to talk about if I have to fill in. But I have several people on the line. In August, Margaret Meixner is coming back. She gave a fantastic talk about planetary nebula last time she was here. Today, in August, she will talk about the life cycle of dust in galaxies, okay? We think about dust as it's, something that we want to get rid of in our homes, but in galaxies, it plays a very, very important role. September, Tom Brown, who was very nice and postponed his talk from last month so we could have Sandy Faber talk last month. He will be giving his talk on the trail of the missing galaxies, the oldest stars in the neighborhood. If you want to find out about, the construction, since you were all here, you know about it, but those of you on the internet, if you want to come down, we have construction on the street outside, San Martin Drive. You have to approach from the north from University Parkway if you come to the talk next month. Our website will tell you all the pertinent details, including the upcoming lectures. We have links to watch it live online, both through YouTube and through our wonderful folks at STSCI Webcasting, which I always like to give them a hand because they work so hard. Thomas Marufu in the back, give him a hand. And also Elena Martin, who is in the back room, taking what they produce and then streaming it to YouTube. Please give Elena a hand as well. All right, thank you very much. We have archives, thanks to these wonderful webcasting teams. We have archives back to, we've been going to YouTube since spring of 2014, and we've been doing this STSCI webcast since 2005. So if you like what you see here tonight, you got a lot more to go through. You got about 11 years of archives to look through. If you would like updates, we have emails. You can sign up for the email on our webpage. How do you find that webpage? Well, if you just say Hubble Public Talks, you'll find it. But if you go to hubblesite.org, go talks, that's our quick go link that will get you directly to that page. As I said, we have email announcements, easiest to sign up on our webpage. But if you don't want to do that, you can go to maillist.stsci.edu and sign up for public lecture announce. Or if you're still lazier than that, you can just hand me your email at the end of the lecture and I'll add you to the list. If you would like to ask us questions, you can send email to publiclecture@stsci.edu, comments, questions, and yet another way to sign up for the announcements. We are on social media as Hubble, as you might expect. Facebook and Twitter and Google Plus and Pinterest and probably a couple other social media outlets that I'm not familiar with. I myself have a video podcast. I'm on Facebook, Google Plus, and on Twitter, but I only use that occasionally because I'm too busy finding other cool things to do. All right. The weather is permitting. We had some thunderstorms this afternoon, but it looks good for tonight. Duncan came in and said, yes, we're going to go to the observatory. So the Maryland Space Grant Observatory across the street. I'll tell you to meet down here after the lecture. If I forget, somebody please remind me, because it'll be a cool night of observing. Well, no, it won't be a cool night. It'll be a warm night of observing, but it won't be freezing cold like it is in December, okay? And you can go across the street, and you must be with the group, okay? No stragglers are going to get in because you have to go through various doors and up various ladders and around these things. So you have to get through, and he has to let you in. So you have to be with the group, okay, in order to get in. All right. Now, my favorite part of the night, news from the universe for June 2016. Our first story tonight, Mars goes retro. Can we get the lights down just a little bit, Thomas? Thank you, because these are going to be a lot of darkness here. All right, so when we talk retro in astronomy, what are we talking? We're talking retrograde motion, okay? So here's the idea. Here's the sun. This is the path of Earth. This is the path of Mars. Not really drawn correctly or to scale, but the point is that Earth moves faster in its orbit than Mars does. So when we are looking at Mars, Mars appears to move across the sky, and then it starts to move backwards across the sky because we're passing by it, all right? And then it starts moving forward again, okay? All right, so Mars moves across the sky, goes back a little bit, and then moves forward across the sky. All right? That when it's going backward on the sky, that is what's called retrograde motion, okay? And it's one of the things that, Ptolemy tried to describe using circles upon circles and epicycles long ago, but was actually fixed when we started to understand that Earth wasn't the center of the universe. Earth being another planet allowed us to understand that, yes, that Mars can do retrograde motion, okay? And retrograde motion looks a bit like this. Now, this is a wonderful series of pictures from a fantastic astrophotographer, Tunç Tezel, whom I met in Brazil this spring when I was giving a talk down there, and he was giving a talk at the same conference. And what he has done here is taken a picture of Mars going through its retrograde motion, and this is basically one picture a week, every 5 to 7 days, he says. All right, you can see the motion of Mars across the sky. So he takes these pictures over the course of many months and then composites them together to show you the motion of Mars across the sky. And you can see how much dedication it takes to do something like this. All right. So this was the motion in the 2012 retrograde. Here it is in 2014. And if I read carefully, it goes from December through to August. So he did this picture over 9 months. And you can see at the time it was going through the constellation of Virgo. All right. And the other thing that he found in the background, that you've got the motion of Ceres and Vesta, the two largest asteroids, also going through their retrograde motion at the same time Mars was doing it. Well, he is, of course, doing it again this year. I got the pleasure of going out in the middle of night in absolute nowheresville, Brazil. Basically perfect, dark nowheresville where, an axe murderer could have taken us and just had their way. Really, just like crazy. Are we going out in a place where we don't even speak the language? And yeah, sure, great. We spent all night out in the darkness, and he was taking pictures of and tracking Mars as one of his things. So he's going to follow it again, and you can say here it's going through the constellation of Scorpius. Okay, all right. And instead of there being Ceres and Vesta, this yellow squiggle here, that's the motion of Saturn. Saturn is also in that field of view as it goes through Scorpius. Now, if you go back to this picture, you can see how Mars is relatively small when it enters and gets really big during its retrograde motion because, of course, that's when it is closest to Earth, right? All right, as the distance from Earth to Mars gets smaller, Mars gets bigger on the sky. All right, that, of course, leads to internet rumors and internet fallacies. Internet is the best way to spread disinformation ever invented. And people saying, oh, Mars is going to get as big as the full moon. That is, of course, totally wrong. And so I found this out on the internet to show you, yes, Mars reached its maximum on May 22nd, which is called opposition, when Mars was opposite the sun and Earth was the closest, and got smaller. But just for comparison, this is the size of the full moon down here, okay? Mars is getting nowhere near the size of the full moon, okay? You'll see all sorts of crazy things on the internet these days, all right? But if you get out there, this was in April. You'll see you can see some marvelous things of Mars, Saturn, and Antares, which is the bright star in the constellation of Scorpius, okay? I went to my software and found out where it is now. Here is the constellation of Scorpius. You can see the Scorpion's tail and the head. Antares here, Saturn over here, and Mars over there. And I asked Duncan if he was going to be able to show that to you tonight at the observatory, and he said, I don't know, I'll check. It might be a little low in the sky. So maybe you'll get to see Mars and Saturn when you go over to the observatory tonight. It also depends upon the time of day, whether or not these have risen above the horizon. All right? But this is Hubble. I haven't mentioned Hubble. Well, Hubble has a tradition, or had a tradition, of photographing Mars at opposition, because of course that's when Mars is biggest. We can get some cool pictures, and the public loves it, okay? I got to tell you, whenever we release a solar system picture, we get a lot of response online, okay? The public loves solar system pictures. So here is a montage of Hubble images from 1995 through to 2007. And you can see that in 2003 was the closest approach, 35 million miles, whereas 1995 was 65 million miles. All right, at these oppositions. So you can see the different years, different oppositions have different distances. This one was around 43 million miles, if I remember correctly, 42, 43 million miles at opposition. So it wasn't as big as it was here, but it was still real cool. And Hubble got a cool picture. The best image you're going to see from Earth, here is Hubble's 2016 Mars opposition. Kind of cool. This is with wide field camera 3, our highest resolution camera. We actually did not take it in 2012 or 2014, so this is the first Mars opposition image we've got with wide field camera 3. Now I said Mars is going retro. Hubble also went retro, because when we got this image, we only had one orbit to take it, okay? So we got the image we got, right? And then we put it up and we said, that looks a lot like the 2001 image. Basically very close to the same face of Mars is showing us in 2016 as we saw in 2001. Although the detail in the 2016 image, we've got twice as many pixels across the face as we did in 2001. But it is kind of interesting that we've gone retro in terms of showing you the same face of Mars that we showed you 15 years ago. Okay, our second story tonight, precision cosmology. Okay, so Edwin Hubble is the namesake of the Hubble Space Telescope, and one of his most famous discoveries was what's called the Hubble Law, or the measured expansion of the universe. Now, we measured the expansion of the universe in terms of the velocity, the apparent velocity of galaxies with distance. All right, and so what we have on the x-axis here is the distance to a galaxy, and on the y-axis is its apparent velocity, as measured by Edwin Hubble. And so the Hubble relation shows that as a galaxy is further away from us, it appears to be moving faster in its recession away from us, okay? So basically, the expansion of the universe means that a galaxy that's twice as far away appears to be moving twice as fast as a galaxy. If a galaxy is moving at a certain speed here, it appears to be moving twice as fast further away. Okay, and so Hubble put this codified this into a scientific paper in 1929. All right, and so the important parameter of this relationship is the slope of this line, and it comes out in some really funky units. Okay, we call this h naught, and Hubble got a measure of about 500 kilometers per second per megaparsec. And kilometers per second is the velocity, megaparsec is the distance unit, okay? And a megaparsec is about 3 million light years, 3.26 million light years, okay? A parsec is it's a unit only an astrophysicist could love. The public likes light years, but sorry, we use parsecs. You don't really need to understand the units, but the point is that he found it was around 500. Okay, now Hubble was using variable stars to measure distances to these galaxies, Cepheid variable stars. And he actually had calibrated his variable stars wrong, okay? He thought he was using one kind of variable star when he's actually using a different kind of variable star. And so he got his slope incorrect, okay? How incorrect? Well, a modern version of this has a slope of 50 kilometers per second per megaparsec. So it's only a factor of 10, okay? Now, we're astronomers, okay? You know, factors of 10, we're in the ballpark, all right? Yeah, even my wife wouldn't agree with me that a factor of 10 is a little bit large, okay? But this was only one version of the Hubble diagram from the modern times. There actually were different interpretations of the data. Bob Kirshner put together this beautiful plot of the original Hubble values were up in the hundreds, and then as we figured out what we were doing, it went down, and it oscillated between 50 and 100, okay? So this is real astronomy, okay? Factor of 2, okay? If it's a factor of 2, it's astronomy, it's all right. So as I was doing graduate school, there was a strong camp of people who said it's 50 kilometers per second per megaparsec, and those who said it's 100 kilometers per second per megaparsec, okay, the 50 and 100. And they didn't agree with each other, and their error bars didn't overlap. And people said, well, is cosmology really a science if one of the most fundamental numbers isn't known to a factor of 2? But along comes the Hubble Space Telescope. And the Hubble Space Telescope had a key project to measure the Hubble constant. We took Hubble, we measured lots and lots of galaxies, we measured the variable stars in them, we measured all the properties to get it down properly, and the result of this, which came out in 2001, was 72 plus or minus 8 kilometers per second per megaparsec. So Hubble finally got something. It's in between the 50 and 100, so both camps could be happy. But it got down to a 10% error, okay? We're going from a factor of 2 error down to a 10% error bar on things, and we're feeling pretty good, okay? And the other thing about this was that this was about the time that the accelerating universe was starting to be accepted, right? The dark universe, right? And this is a diagram I found on the internet the other day. Taking the dark universe and comparing it to a pint of stout, where 73% of it is dark energy, 23% of it is dark matter, and by the way, various models have that as 74-24 or 72-24 and other things. And then the 4% of the normal stuff is mostly interstellar gas and a little bit of stars, planets. And the point of this diagram, I think, was that, hey, everything we know is just the foam on the tip of the on the top of the beer glass. But it gets across the idea of the dark universe, and if you take these cosmological models and you figure out what the Hubble constant has to be today, the H0 today, to fit with these, you get around 70 kilometers per second per megaparsec. Yes, we're agreeing a cosmology is working. And a lot of this dark energy stuff was done by studying distant supernovae. So here is a galaxy at a really large distance, and here's that galaxy later where there is a supernova. And because the supernovas are standard candles, we can use those to measure the distances to these very far away galaxies. So we had these variable stars nearby, and we had these supernova really, really distant, okay, as two ways of measuring distances. Wouldn't it be great if we could combine them? Of course it would be, and that's the point of this story, that a new group of researchers decided that they were trying and really beat down the error on the Hubble constant by looking at galaxies where there was a supernova. See that blue mark? That's where a supernova was found in this galaxy, a type 1a supernova, as well as find variable stars in those galaxies. These are all these red circles. And so they got a collection of these galaxies that had both variable stars and supernova, so they can tie the distance scale nearby with the distance scale far away and reduce the error in our understanding of it. Because remember, we had about a 10% error in H0. This new result is a more precise result where they even quote a decimal point, 73.2 kilometers per second per megaparsec. That's audacity in cosmology, okay? When you can start quoting 0.2, right? When we were able to say the universe is 13.7 billion years old, that was, audacity in cosmology. Well, they have the same audacity here. Whereas the cosmological results from the cosmic microwave background surveys said WMAP has it around 70 and Planck has it around 67. But that brings up a puzzle, because the formal error on this result is a 2.4% uncertainty, whereas the values are 5 and 9% higher than what we get from the very early universe. So the local universe, the measurement of the expansion rate right now in the local universe disagrees with what we would predict from the early universe. knowing from the early universe, we're predicting the components of the universe and how the universe would expand. So it's, as they said in the press release, it's like building a bridge from two sides, all right? And they're building it from the local side, and they're building it from the early universe side, and they're coming in and they're not connecting. They're not connecting it exactly, right? So something is still missing, because if this result holds up, then what we predict from the early universe isn't what we're seeing in today's universe, right? And that causes a problem. So maybe, I'm actually not too worried myself, because there's a lot we don't understand about dark energy, right? Okay? We don't even know what the dark matter in the universe is. And in the press release that they were talking about, they said, well, there could also be this third component called dark radiation, okay? Undiscovered particles that could account for this. But generally, our physics works really well once you specify the cosmological model that we feel like we should be within these error bars, okay? I can't tell you the result of this. I can say stay tuned, that the more we know about the universe, the more we learn that there is more to know about the universe, okay? So we have beat down the error. We're finally getting into what we call precision cosmology, but that also means when you've got precision, you can also have disagreements, and it can bring about those disagreements. So it's really kind of cool, because, when I was doing my PhD in cosmology, people were like, yeah, you guys really don't know what you're talking about. Now that we know what we're talking about, we're finding out that there's still a lot more to learn. All right? And so that's our news from the universe for June 2016. Our feature speaker, questions. Did you have a question, Peter?
Could you repeat that?
Which part? All of it. Okay. All right, our featured speaker tonight. PowerPoints. There we go. Is Nikole Lewis. And she got her undergraduate degree at Worcester Polytechnic Institute up in Massachusetts. She did her master's at Boston, and she got her PhD in planetary science from Arizona State University. She did a postdoc up at MIT before coming here to a Space Telescope Science Institute, where her most important role here is working on NIRIS, is it? NIRIS. I know, but I'm just giving, because ISS, the near infrared imaging spectrograph, single source spectrograph. All right. Keeping all the acronyms in your head is really difficult, okay? On the James Webb Space Telescope. But even cooler, she is the lead in the Transiting Exoplanets team study group lead for James Webb Space Telescope. So she'll have a lot of say and influence in studying planets around other stars, and she'll tell you about that tonight. Ladies and gentlemen, Nikole Lewis.
Can you hear me okay back there? So do I need to hit this box? I'm on 4. I'm on 4. There we go. All right. Well, good evening. I'm delighted to be here today. And I'm even more delighted to tell you about our current and future efforts to study planets outside of our solar system. Okay? And I'm going to start this journey by giving you a brief history of the field of exoplanet science. Yeah? Is that better? Okay. Okay. So the field of exoplanet science is a relatively young one. It was really born in the mid-90s, so it's not much older than I am. So what I have plotted here are the number of planet detections as a function of discovery year. Okay? So again, we began in the mid-90s. To date, we have more than 3,000 confirmed exoplanet detections. And as you can see from this lovely little bar chart, they sort of trickled in for a while, and then you see this sudden exponential climb. And I fully suspect that this exponential climb will continue for the foreseeable future. So next year, if I'm giving this talk, I may say we have more than 6,000 confirmed exosolar planets. We shall see. The colors on these bars are represented by the method in which they were detected. So this green is what's called transits, and the red is the radial velocity. And I'm going to focus on these two methods today because, as you can see from this bar chart, They are the predominant method in which we detect exoplanets. These other methods are equally as interesting, but I don't have time to focus on them, except for this last one, imaging, which I'll touch on towards the end of the talk, because this is where we really are heading in the future. So now you know the brief history of the field of exoplanet science. Now let me introduce you to the cast of characters. This is our current population of confirmed exoplanets. And what I have plotted here on the y-axis is planet mass in Jupiter masses. So we actually study everything relative to the mass of Jupiter in our own solar system. And orbital period here is on the x-axis in days. So, Earth's orbital period is about 365.25 days. So if I add our own solar system planets to this plot, this is what they look like. So we have Mercury, our closest end planet, 88-day orbit, Venus, Earth, and Mars, Jupiter, Saturn, Uranus, and Neptune. Now, if you look closely, you may notice something. This whole mess of exoplanets looks nothing like what we see in our own solar system. Okay? In fact, I'm going to draw a line right here. This is an orbital period of 1 day. Okay? There are planets that exist in orbital periods of 1 day or less. So they're orbiting so close to their host star that their orbital period and actually their rotational period, because they are so close, entirely locked, is equal to 1 day. I'm going to draw another line. This is 10 days. This is a 10-day orbital period. We're still well within the orbital period of Mercury in our own solar system. Now, as you can see, we have a very large variety of exoplanets in this range. And like I said, a lot of these are very close-in planets. They're assumed to be tightly locked to their host stars, meaning that they present the same face to the stars that go on their orbit. This means they have permanent day and permanent night sides. Okay? So I'm going to put a little bar up here to give you an idea of the range of temperatures for these planets. So when you're in a 1-day orbital period, you're pretty close to your star. You're going to have temperatures exceeding sort of 5,000 degrees Fahrenheit. Basically, if you're a small rocky planet, you're going to have a liquid lava surface, hot enough to melt iron. And then they go out to sort of more nominal temperatures we see in our own solar system, something like negative 300 degrees Fahrenheit. Okay? So we have a very diverse population of exoplanets. And I want you to, if anything you take away from this talk, is that they look nothing like what we see in our solar system. So how did we find all of these wacky planets around other stars? Well, let me tell you a little bit about the methods we use to detect them before we go on to our further exploration of these systems. And the first method I want to talk about is called the radial velocity method, or RV method for short. And this has been a very prolific method. It's discovered 586 planets to date. It is predominantly done with ground-based observatories. And what these ground-based observatories do is they take advantage of the fact that when you have a planetary system, the planet and the star actually orbit around a mutual center of mass. So on this little plot here, you'll see this star has this tiny little orbit, and this planet has a larger orbit. And so if we watch this movie go forward, you'll see these guys go around in their orbit, and then the plane's going to turn towards you. And what you'll see is the star moving away from you as it goes around in its orbit, and then towards you. So this is going to create a red shift as it moves away, and a blue shift as it moves towards you. And you'll actually see these shifts in the stellar spectrum. So with the radial velocity method, you don't actually detect the planet directly. What you do is you detect the effect of the planet it has on its host star. And because you're measuring this tug of this blue shift and red shift, which is a gravitational effect, you can actually measure the mass of the planet in this context. So this is a really important method because it's one of the few ways in which we can determine the mass of exoplanets. Now the RV method, this is just a brief history. What I have here on the y-axis is planetary mass, again in Jupiter masses and year of discovery. So in the early days, in the early mid-90s, they were really finding a lot of Jupiter-sized planets in these really short period orbits. So again, these are what we like to call hot Jupiters. Now, these were very surprising. Jupiter in our own solar system is located at 5 AU. That's kind of where we assumed all gas giants would be, because that's where they formed beyond what we call the snow line. To find a bunch of Jupiter-sized objects this close to the host star was confusing, and it actually took many, many years to get people to believe that this was even true. So as time progressed, though, technology improved. So both the capability of our ground-based instrumentation, but also our ability to reduce the data increased. So as you see, So as you see, As time went on, and now we're here in 2016, we're actually able to measure the mass of Earth-sized planets. Now, these are still typically on very short period orbits, but we're getting there, and that's the point. And that future work will get us even closer to measuring the mass of a true Earth twin. So the other important detection method is called the transit method. And this one's actually really simplistic, okay? You again have this planet along in this orbit around its host star. And with the transit method, what you rely on is that the orbital inclination is such that we actually see the planet pass in front of its host star. Okay, so we're looking from Earth, and we see the planet go in front of its host star. And what that does is actually creates a little dip in the combined light of the system. So here's the planet outside the host star, it goes in front of the host star, and then comes out the other side. This is very similar to the recent transit of Venus that maybe you've seen in the news. Now, the great thing about the transit method, beyond its simplicity, is that you can use the depth of this transit right here, so to determine the relative radius of the planet with respect to the host star. So the radial velocity method gives you a mass, and the transit method gives you a radius. So again, the transit method history, you have a lot of early struggle here, trying to use ground-based observatories to look for these tiny little signals as these planets pass in front of the host stars. And again, they were mostly finding hot Jupiters using this method. But time went on, and rapidly we're down now into the era where we're finding planets that are actually smaller than Earth. And the reason why you have this big buildup right here is due to the Kepler mission. Okay? So the Kepler mission, which was launched in 2009, had a very simplistic mission. It went up with a bunch of CCDs, and it stared at one patch of the sky continuously for almost 4 years. And it just sat there, monitoring all the stars in the field, watching for these transit events. So it's just looking for any planets passing in front of the stars. And over time, what they're able to do is find planets on longer period orbits, but they're also able to use phase-folded information to progressively detect smaller and smaller planets. And recently, there was a new release of planets that had been validated, and they moved from what's called planet candidates to confirmed planets by Kepler. And what we have here is the population of Kepler planets, so this is the number of planets on the y-axis, versus their size bins here on the x-axis. And so for comparison here, there's solar system planets, Jupiter and Saturn, so this is their bin, Neptune and Uranus, these are their bins, and then Earth, Venus, Mars, and Mercury down here. And what I want you to notice is this giant blob of planets that exist in between the size of Neptune and Earth in our own solar system. These are what we fondly refer to as sub-Neptunes or mini-Neptunes and super-Earths. These are types of planets that are actually the most populous type of planet in our galaxy that don't exist in our own solar system. So they have no solar system analogs. We have no way to sort of use a picture of Jupiter to figure out what they look like. So this was another grand mystery. The first mystery was, how could there be a Jupiter so close to its host star? The next grand mystery was, what are these planets in between the size of Earth and Neptune? So as I said, with the radial velocity method, you're able to get a mass, and with the transit method, you're able to get a radius. And this allows us to do our first, what I would consider, characterization of these planets. So we've gone beyond knowing, yep, they're there, to being able to say something about their characteristics. And we can do that by sort of plotting them on this radius. So this is Earth radii versus mass diagram. And again, these colors are the discovery method, transits, radial velocity. Don't worry about the purple at the moment. And I'm going to plop our own solar system planets on here. Saturn and Jupiter are actually off in this direction. But I want to highlight this transition region. So we have Neptune and Uranus right here, which we know are gas giant planets. They're dominated by hydrogen and helium in their atmospheres. And then you have all the terrestrial planets down here. So there's this transition that happens that you go from being hydrogen, helium dominated into being what we would consider rocky planets. So there have been rocky planets discovered. We do know sort of the bulk composition of those planets. Now looking at this plot, you may notice there's not 2,500 green dots here. I don't take the time to count them, trust me. And the reason is that the Kepler mission was very, very successful, but part of its success was that it actually looked at a lot of stars that were kind of faint. Because you're looking at the single patch of sky, you take the stars that you have. It's actually kind of hard for radial velocity surveys to follow up many of those stars and do those mass measurements. So there are planets that have been detected with Kepler for which we don't currently have masses. So we don't know what their bulk compositions are. All right. So that was a brief introduction to how we detect exoplanets and how we do our first step at characterization through determining their bulk composition from our mass radius diagram. Now let's go one step further and let's start to probe them just a little bit more. But first I'm going to give you a brief introduction to spectroscopy, because this is how we go one step further and probe exoplanets. So if you have a light source, say the sun, or a distant stellar object, and you look at it through a telescope with a spectrograph or just a prism, what you'll see is that that light is spread out in a rainbow that you're kind of used to, okay? So this is what the stellar light looks like as a function of wavelength. Now, if you have some intervening material, in this case a gas nebula, and you look at the star through that gas nebula, what you'll see is absorption features imprinted on your perfect rainbow. And what's that telling you is that it's giving you information about the composition of the gas. So there could be molecules or atoms in this material that are absorbing that light and therefore giving you these dark regions you see here. So this is an absorption spectrum. You could also just look at the gas nebula, from an off-angle degree, not through the stellar host there. And then what you see then is an emission spectrum. So this again gives you information about the composition of this gas nebula. You'll notice that these emission lines correspond to these same dark lines in the absorption spectrum. So this is two ways in which you can get information about the composition of your gas nebula. I'm going to throw a planet in the middle because that's what we're doing. But they don't make any nice diagrams to explain this with planets in the middle. But fundamentally, this diagram is what's going on with any planet that's in a transiting exoplanet. So a planet that we see pass in front of the host star as seen from Earth. Okay? So you have the same sorts of phases. So as the planet goes in front of the host star, that stellar light is going to be filtered through the planet's atmosphere. And then imprinted on that stellar light is going to be signatures of the composition of that planet's atmosphere. So molecules, atoms, perhaps signatures of clouds or hazes as well. Now, as the planet goes around in its orbit, it will also do what's called a secondary eclipse, or just an eclipse, and that's when it's going to go behind the host star. And you'll see a dip in the combined light of the system. And this will give you an estimate of the thermal radiation from the planet, if you're infrared wavelengths, or the scattering properties of the planetary atmosphere if you're at visible wavelengths. In addition to this secondary eclipse event, you can actually just watch the planet go around in its whole orbit. And because most of these planets are tidally locked, much like the moon is tidally locked to the Earth, you can look at the different phases of the planet as a function of time. And this will give you an estimate of the longitudinal thermal distribution of the planet. So I just wanted to give you an idea of the strengths of the signals that we're looking for in these cases. So for these transit or transmission measurements, basically your signal strength is going to scale as the ratio of the planetary radius to the stellar radius squared times this scale height. And the scale height is just a measure of sort of the fluffiness of your atmosphere. Is it extended or is it compressed? And typically we're looking at signals on an order of 1/100th to 1%. So these are tiny, tiny, tiny signals that we're looking for. It gets even worse as you go to the eclipse measurements. And again, I'm assuming infrared here, and this is when it tucks behind the host star. And the strength of this signal depends on the radius of the planet with respect to the star squared, and also the temperature of the planet with respect to the temperature of the star. And here, basically, we're looking at something, 1/100th of a percent to 1/10th of a percent. The phase curve, so this is as a function of orbital phase, is always less than your eclipse step. So again, you're looking something on 10th to 100%. And these very precise measurements largely require that you do these sorts of observations from space-based instrumentation. It's the only way that you can get the stability. When you try to do these sorts of measurements to probe the atmospheres of exoplanets from the ground, we have our own atmosphere to contend with that creates all sorts of extra noise that prevents us from getting to these very, very small signal levels. So here's what a transmission spectrum looks like in practice. And the first detection of an exoplanet atmosphere was actually achieved with the Hubble Space Telescope. And what was done is they looked at the planet as it passed in front of its host star using the STIS instrument, and they looked for signatures of sodium and potassium in the planet's atmosphere. And so this is sort of the spectrum that they got. So this is wavelength increasing in this direction. And the way that we measure these spectra is actually as a function of a change in the planet's radius. Okay? So basically, the planet will appear larger at certain wavelengths, which means that it's absorbing more of that incoming stellar light. So it has a lot of sodium or potassium in its atmosphere. So this is what it looks like in practice. So what we actually measure is the planetary transit. So this is what a transit looks like. Here's your planet outside of the stellar disk, and then it goes, this is called ingress as it goes into the stellar disk. Now it's crossing the stellar disk and then coming out the other side. And you can make these measurements as a function of wavelength, again looking for those changes in the radius of the planet, so changes in the depth of the transit as a function of wavelength. And that allows us to then turn it into a spectrum that has, in this case, very strong sodium features. So this is what we actually measure from observatories like the Hubble Space Telescope. Now, so that was the first measure of an exoplanet atmosphere for HD 209458b. Yes, we don't have very good names for our exoplanets, but that was a decision made well above my pay grade. But we do have a number of transits for a lot of gas giant-sized planets, what we commonly refer to again as hot Jupiters. And using combined, figure out where my, there we go, pointer is. Using the combined data from the Hubble Space Telescope at visible and near-infrared wavelengths, so that cover this region, and the Spitzer Space Telescope at longer wavelengths, this is infrared measurements, we've been able to measure water, sodium, potassium, methane, carbon monoxide, titanium oxide, and clouds and hazes in these planetary atmospheres. Clouds and hazes have become particularly interesting because what they do is they serve to mute these features in the transmission spectrum. So you'll see for some of these planets, like WASP-17b, you have very strong sodium and potassium features. Or in other cases, say for HD 189733b, you don't see those features. And that's because they're being muted by cloud and haze layers in those planetary atmospheres. So that's for hot Jupiters. As we begin to make further observations, we've moved to smaller and smaller planets, and we've started to encounter what we call the super-Earth problem. Okay? Again, we know what a gas giant planet looks like, thanks to Neptune in our own solar system. We know what Earth looks like. We have no idea what these wacky mini Neptunes and super-Earths look like. They could have a broad range of atmospheric compositions. They could have hydrogen and helium-dominated atmospheres, maybe with an enhancement of heavier elements. And this means that we don't have a good grasp on the chemistry that's happening in these planets' atmospheres. We don't understand well what cloud and haze formation looks like in these planets' atmospheres because we have no solar system analogs. So when we do transmission studies of super-Earths, we have a number of different cases we have to rule out. It could be that they have a clear hydrogen-helium-dominated atmosphere similar to a hot Jupiter, in which case the starlight will happily just pass through the atmosphere and we'll see a spectrum much like I showed on the previous slide. However, it's also possible that they could have a water-dominated atmosphere, and this would be an atmosphere that has a smaller scale height. So again, hydrogen-helium-dominated atmospheres have a large scale height, they're puffy. Water-dominated atmospheres would have a smaller scale height, so they would be much thinner. So it's possible we wouldn't be able to measure much of a deviation here. Most of the starlight would either pass above this atmospheric level. It's also possible that they could have very thick cloud or haze layers that would also mute out our transmission spectrum features. And this is exactly what happened to probably the most famous super-Earth planet, which is called GJ 1214b. So, I know. I could rename them Bob or whatever if you want, but we'll call it GJ 1214b for now. So basically, more than 60 orbits of Hubble time was devoted to the study of the atmosphere of this planet. And again, what they do is you can look at the transit event as a function of wavelength. So here's the planet outside the stellar disk, here it goes across and then down, here's in the middle of the stellar disk, and then egress over on this side as a function of wavelength. And they were able to beat down the noise to the 30 parts per million level. So basically, if there was a signal there, it would be tiny, tiny, and you could detect it. But what they actually found was data that are consistent with a flat line, which means they were actually able to rule out a whole host of other scenarios for the planet's atmosphere, including a water-dominated atmosphere, a CO2-dominated atmosphere, and a methane-dominated atmosphere. Instead, what they're seeing is that this planet is shrouded in very, very thick clouds and hazes. They are basically obscuring all of the spectroscopic features of this planet. A number of other super-Earths have also been looked at, and the story seems to be the same. Now, there is hope. These super-Earths that we've been probing recently tend to be in a temperature regime such that there's a lot of methane hanging around in the atmosphere, which is very, very good at creating longer chain hydrocarbons, which create hazes. So it's possible if we start looking at these planets at hotter or cooler temperatures that we won't run into this really, really thick smog layer, basically. All right, so that was transits. Now let me tell you a little bit about eclipses. So again, eclipses is when the planet goes behind the host star, and they're critically important because they allow us to take the temperature of the planet. That's why I put a little thermometer in the planet, because you're measuring the thermal emission at infrared wavelengths from the planet with respect to its host star. And here are secondary eclipse measurements for the planet GJ 436b. This is a Neptune-sized object at various wavelengths taken with the Spitzer Space Telescope. So again, when you're looking for thermal emission, you tend to need to go to longer wavelengths, which is the regime of the Spitzer Space Telescope, and in the future, the James Webb Space Telescope. So you can see these eclipses at various wavelengths, which again allow you to produce a spectrum, but more importantly, give you information about the thermal structure of the planet. So from these measurements, we're able to know the approximate temperature of the planet, about 800K or so, which gives us critical information for understanding the chemistry at work in this planetary atmospheres. So having both transit and eclipse information is very complementary and is really the only way to get a complete picture for what's happening in the planet's atmosphere. Now, you can go one step further and do what's perhaps my favorite thing to do, which is just to monitor the planet throughout its orbit, or to make a phase curve observation. Again, these are tidally locked, so we can look at the phases of the planet as it goes around its orbit. And what you see here is a half-orbit phase curve measurement for the planet HD 1897333b, taken with Spitzer at 8 microns. So this is relative flux. So we measure everything in relative flux. It actually makes our lives easier. We don't really care about absolute calibration of data because we're measuring everything relative to the host star flux. So you'll see here this is the transit event. So again, the planet passes in front of the host star and you see this large dip. It goes along, and then here is the eclipse. This is when it ducks behind the host star. Now, if you zoom in this region in between transit and eclipse, down here, you'll see that there's actually some structure here, and that you can fit more or less a sinusoidal modulation. And perhaps more importantly, the peak of that sine curve is located right here. And the reason why that's important is it allows you to make a rudimentary map of the thermal distribution on the planet's surface as a function of longitude. So you're able to figure out at what longitude the hottest point in the planet is. Again, these planets are tidally locked, so we assume that all of the energy is being deposited at high noon on the planet, so straight down. But what we're actually seeing is that the peak of the planetary brightness occurs offset from that, so just to the east of the substellar location. And this was actually our first detection of weather in an exoplanet atmosphere, because this offset can be explained by the presence of very strong winds in the planetary atmosphere. So what those winds are doing is they're taking all of those parcels of gas that are heated up near the substellar longitude and they're moving them downwind. And this was actually predicted using general circulation models for exoplanet atmospheres. So what you have here is a GCM for a hot Jupiter. Here's latitude, North Pole, South Pole, longitude from substellar, so here's high noon. And this is a robust prediction. We predict that most of this energy will be transported downwind by winds that are on the order of 1 to 2 kilometers per second in these planetary atmospheres. Okay? They are still subsonic if you do the calculation, but still very, very, very fast. Now, that was done with Spitzer at 8 microns, so a single big photometric bandpass. You can do phase curve observations with Hubble as well and do them spectroscopically, and this was done with the Wide Field Camera 3 instrument, which focuses on the water bands in the atmosphere. So I'm going to start up this movie, and what you can see is as this globe goes around, you'll see the emission spectrum change. That gives you an idea of the distribution of water on the planet, and also the retrieved thermal profile of the planet. So this is the temperature of the planet here on the x-axis as a function of pressure. So here's the top of the planetary atmosphere, and this is going down towards the core of the atmosphere. So it'll spin up. You'll see the hot point come around. You'll see what the thermal profile looks like. You'll see the enhanced water emission. And then as you go around to the night side, the water emission drops off. So we're able to measure the abundance of water on this planet as a function of longitude. We're able to measure the thermal structure of this planet as a function of longitude. And these sorts of measurements are critical for understanding the climate of exoplanets. Okay. So a quick sidebar about blackbody emission. So our sun emits light in the visible, right? So it's about a 550 K blackbody. So these are curves for different temperature blackbodies. Things I'm more familiar with, which are planets, are way down here, sort of 1,000 to 100 Kelvin or so. But stars emit predominantly at visible wavelengths. Now, the peak of the stellar spectrum, again, is in the visible, and planets, in fact, scatter the stellar light from their hosts. So there is a component of what we're looking at from planets that's actually scattered stellar light. And if we look at how that compares for different types of planets, you'll see that for these hot Jupiters, we have thermal emission, which is this part over here that peaks around, say, 2 microns in the infrared. But you also have a significant component of the planetary spectrum here at visible wavelengths, which is due to scattered starlight that you see then from the planet. So here's a warm Earth. Now in this case, as you go to these smaller planets, the thermal emission is a much smaller part. They tend to be dominated by the scattered light, so the light that they scatter from their host stars. So there's a benefit to looking at both thermal emission and scattered light to gain insights into the planetary atmospheres. And we were able to do that actually using the Kepler Space Telescope. So it turns out if you're going to sit there and stare at something for 3 years, sometimes you're going to catch something that looks like a phase curve. So again, I showed you a phase curve before that was at infrared wavelengths where we were looking at thermal emission as a function of longitude. The Kepler instrument has a bandpass that's centered into visible wavelengths. So what we're looking at is scattered emission from the planet as a function of longitude. So here's the little phase curve measurement. And what that allowed us to do was to actually map the clouds on an exoplanet atmosphere. And this is the planet Kepler 7b. And what we found is that these clouds are actually sort of located on the western terminator and then dissipate as you go across here to the east. So these are sort of mid-morning clouds, and as the planet heats up, they dissipate. I think it's important to note that these clouds that form in this planet are nothing like the ammonia clouds that we see on Jupiter. These are silicate clouds. So a lot of these hot Jupiters actually have cloud species that are common rock-forming materials here on Earth. Okay, so the temperatures are so extreme that basically you have rock rain.
What species?
Silicates. Instatite or forsterite are the names, but think sand, basically. So I've given you sort of a tour of all of the wonderful ways we've been able to probe giant exoplanets and begun to probe super-Earths. And I want you to at least walk away with the feeling that even though we're chasing habitability in the end, that these sorts of studies are very worthwhile. And the reason that they're worthwhile is that they give us a lot of information about planet formation, evolution, and theory. So giant planets are really a fossil record of the planet formation in a solar system. So by probing the composition of these giant planets around other stars, we're able to understand their compositions, how clouds are formed, and trace that back to the formation of all the planets in the system. So this is work that will continue to be done both with Hubble Space Telescope and in the future with James Webb. But I'm imagining many of you are kind of wondering, when are we going to talk about probing Earth life on another planet, or probing Earths? And I'm going to put Earths in quotes because I think the definition of Earth is a little bit vague here. So I have to start by talking a little bit about the habitable zone and what we mean by an Earth twin. So what I have plotted here is the mass of the star relative to the sun. So these are different stellar types. We have M-type stars, these tiny ones down here, G-type, which is our sun, and up from there. So here's our solar system. This is the radius of the orbit relative to Earth. And we have something that's called the habitable zone, which has been defined more or less by the sort of orbital region where liquid water could exist on the surface of the planet. And in a solar system like ours, around a G-type star, this occurs about around 1 AU. Earth is nicely in the middle of this magical habitable zone. Venus and Mars are on either side. So there are many definitions of the habitable zone that actually expand it this way or out this way to infinity, but we'll focus on the more common definition that simply you have to have liquid water existing on the surface. Now, I'd like to point out that as you go down to these M dwarfs, these cooler stars, that habitable zone becomes closer and closer to the host star. Okay? So instead of, if you were trying to, say, probe a planet in transit around a G-type star, you'd only have one opportunity a year to catch that, right? We orbit our sun once a year. Whereas you get down into this regime, you have many, many opportunities. These planets are in shorter period orbits, okay? So what we want to do is to be able to look at rocky planets that transit their host stars and detect something that looks like an Earth spectrum, okay? So this is the relative transmission of Earth as a function of wavelength. So this goes basically from 1 to 20 microns. This is predominantly an infrared spectrum. And it highlights a number of the key chemical species in Earth's atmosphere: water, CO2, ozone, O2, and methane. I think it's important to note that a lot of the chemical species that we see in our atmosphere are the result of biologic activity here on the surface. So trees, people, etc., create chemical disequilibrium in the planet's atmosphere. So you can use this chemical compositions, in particular the presence of O2 and ozone, as a potential biomarker, although there are many other biomarkers potentially out there. Now, if you were looking for Earth transiting a sun-like star, you'd be looking for this 0.0084% transit, tiny, tiny signal. But if you were looking for an Earth orbiting an M-type star, it would be 0.1% signal. Much more achievable. So really, the future of transiting exoplanet science relies with what I call the dream team here. And that's the Transiting Exoplanet Survey Satellite TESS, which is scheduled to launch in 2017, and the James Webb Space Telescope, scheduled to launch thereafter in 2018. And the reason that they're the dream team is that TESS is going to use a survey strategy to do a full sky transit survey. So unlike Kepler, where they stared at one tiny patch of the sky and waited for transits, TESS is going to do the whole sky. And they've devised it such that depending on where you are, you have different periods, basically different portions of time you'd be staring in that vector of the sky. So here near the ecliptic, you have a 27-day window, which means if you see any transits in that 27-day, great. And as you go up towards the ecliptic poles, these become longer and longer with up to a year up in this region, which happens to correspond with the James Webb Space Telescope continuous viewing zone. It's a very well-designed observatory. So the hope is that with the TESS mission, we're going to find a lot of transiting exoplanets around bright host stars. And that means two things. It means that we can do radial velocity follow-up and figure out their masses. And it also means that we can do spectroscopic characterization of their atmospheres. So currently, this is the planet population with what we call the J-band magnitude greater or less than 10. So this is sort of our indicator of brightness. So we have some Jupiters, some sub-Neptunes, and a few Earth-sized planets. But after tests, we'll be filling out this parameter space much more fully. And we'll still be looking at planets in orbital periods sort of between 1 and 100 days. Some of these will be in the habitable zones of their host stars because the TESS mission is really focused on M-dwarf hosts. Okay? So with JWST, we'll get our first insights into rocky planet atmospheres. So far we've been struggling with super Earths and mini Neptunes and getting clouded out. But with JWST, we're going to be able to look at progressively smaller planets. And this is one in particular called GJ1132b. I know, another great name. But this was the first sort of truly Earth-sized planet discovered that we could characterize with JWST. And this will be done in transmission with the NEARES instrument. So this is the instrument I work on. And then it would also be looked at in emission, so again, eclipse spectra using the MIRI instrument. And this combined information would allow us to detect the presence of a CO2-dominated atmosphere, so something with a tiny scale height, but we'd still be able to detect it. It could also potentially reveal the presence of things like ozone or O2, which would give us information about the potential habitability of such a world. So there are limitations to transits. You got to have something in a short period orbit, or you don't have a lot of opportunities to look at it. It's best to look at them around M-dwarfs, which is not a regime that we're familiar with, living around a G-type star. So how do we go beyond transits and probe Earths that are more similar to Earth in our own solar system? And the way that we do that is using direct imaging. See, I told you this would come back. So direct imaging is perhaps the simplest approach to detecting and characterizing exoplanets. And the reason is that you have some bright star, and you, come on, where'd it go? Put something in front of it. And then suddenly you can see something that's not so bright next to it. This is called coronography. So you just have to figure out a way to block out the star's light such that you can see the much fainter planet next to it. And this method has actually been used to detect about 41 planets to date. And here's an example. This is the HR8799 system that was detected from a ground-based observatory. They blocked out the starlight, and then they were able to see planets B, C, and D around this host star. This was done at near infrared wavelengths, and the reason is because most of the directly imaged planets discovered to date have been measured via their thermal emission. So these are young Jupiters, so these planets just form. They have all of this sort of latent heat of formation, so they're radiating at very high temperatures, 1,000 to 2,000 Kelvin. Okay. So in the future, we're going to have a coronagraph in space aboard the Wide Field Infrared Survey Telescope, or WFIRST. Now, Hubble and James Webb both have coronagraphs, so here's JWST and HST, but these are sort of simplistic coronagraphs. They're little pieces of metal that you can put in front of the star. There's ground-based facilities such as what's called the Gemini Planet Imager, and in the future WFIRST, that will use these sophisticated optical systems to better control the suppression of the starlight. So they use all these little deformable mirrors and all these fancy optics to get us down to lower and lower contrast levels. When I talk about contrast levels, what I have here on the y-axis is the planet-star contrast. So this is basically the relative precision you need in order to see the planet next to the host star. So we're at 10 to the negative 3 up here, down to 10 to the negative 10, which is what you need to measure to detect an Earth around a G-type star. So with WFIRST, we'll actually be able to get down to this 10 to the negative 9th to 10 to the negative 10th contrast level. We'll be able to characterize actually some planets that have been detected with the radial velocity method. So we already know there are planets out there that we can image and spectroscopically characterize with the WFIRST mission. There's also a whole host of planets that we could potentially detect with the WFIRST mission. So we'll be getting more of those little blobby pictures of planets sort of in the mid-2020s when WFIRST launched. So this is what the W1 spectra will look like. So again, what we expect to have with W1 is we're going to suppress the starlight, and then we'll see these planets popping out, much like you saw with the HR 8799 system. But there will be a spectrograph aboard, which means then we'll be able to take the spectrum of the planet. And what we'll see is, in the case of gas giant planets like Jupiter, methane and water. Now, most of the planets that we're actually going to be able to detect with W1 are going to be Jovian-sized planets that are about 1 AU from their host star. So these are going to be Jupiters that are at the same temperature as Earth. So they're going to have very dense water clouds, which are going to give us a really nice, strong signal. But we'll be able to measure methane and water abundances, which are going to give us clues to the underlying composition, and also the planet formation and evolution history. Now, so W1 is going to do a great job of giving us spectra of directly imaged sort of Jovian-sized planets. It will give us our first detection of directly imaged super-Earths in photometric band passes. But beyond that, we really want to get to the place where we can make a picture like this. So we want to get to the technology to get to the point where we could suppress the starlight around a G-type star such that we could see Venus, Earth, and Jupiter. Okay? This is the picture that we're aiming for, and the technology is heading in that direction. And then if we're able to put a spectrograph in there, we can start to measure the spectra of, say, an Earth-type planet in green, or maybe a Venus, which actually has a very strong signal thanks to all those really dense clouds on that planet's atmosphere. And this will be our first chance to really look for biosignatures of planets that are in their habitable zones around sort of nominal G-type stars. So this will be our first opportunity to study what I would call true Earth twins outside of our solar system. Now, most of the methods that I talked about in terms of coronagraphy relied on using internal coronagraphs. So either a little piece of metal that blocks out the host star, or fancy optics that control the wavefront and then use that to suppress the starlight. There is another option, and that's an external coronagraph. And so I'm going to start up a movie here to show you how we could study other worlds with the help of a star shade. I think it's going to start. I'll let you read while I take a drink. So again, this is an external occulter. So it's not part interior to the telescope. It's actually separate from the telescope. They would be launched together, and then there would be formation flying required for this to happen. And that's gigantic, in case you're wondering. So this would be like a 2-meter telescope, so, 20, 40 meters. So again, and this shape has been designed specifically to give the best suppression of starlight in this case. And it's one of the best ways to get really close to the host star. So it's what we call the inner working angle. So star shades are great at doing that, and they're actually currently being built. Okay, there's a number of small-scale models, but they're also working on the technology of how do you unfurl some giant thing like that after you've launched it into space. So this is where the technology is heading. I think in my lifetime, we will see a star shade in space. And we'll be taking pictures of solar system analogs. So we'll take our first pictures of another Earth-sized planet, 1 AU from a G-type star, sometime in my lifetime. And we'll be able to tell what those atmospheres are composed of. And then we'll be able to start having great debates about whether the atmospheric composition is indicative of life on the surface, which I'm sure will be great debates. And it will require a large number of detections for us to have a large enough sample for us to start to understand what is and is not a biomarker. So this is where the field is heading in terms of exoplanet characterization. Right now, we're really focusing on transits because that's our best opportunity to probe their atmospheres. We've done a lot of work with giant-sized planets, and we've begun to move to smaller and smaller planets. But there's a lot of work to be done. The James Webb Space Telescope will characterize the atmosphere of hundreds of exoplanets, and potentially ones that are in the habitable zone of their host star, be it an M-dwarf star. So the next sort of 20 years are going to be pretty exciting. So I hope everyone stays tuned. Questions? There's someone in the back there.
Any explanation on why you're finding more of the tidally locked planets, and also any capability of finding asteroid belts around other?
Yeah, so the first question was, why are we finding so many tidally locked planets? That's really an observational bias. Those are the easiest ones to find. So for the RV method, if you got a giant Jupiter close, or even an Earth-sized planet, very, very close to the host star, that gives you a bigger signal than an Earth located farther away. So that's the gravitational tug. Same thing with the transit. The closer the planet is to the host star, the more likely it is actually to transit, and the more frequent the transits are. So a lot of that is observational bias. Now, we have reached a point with the radial velocity technique that we've begun to probe regions that are similar to Jupiter and Saturn in our own solar system, and we've actually started to see a drop-off in the planet population. So there does seem to be some sort of hole in parameter space with a lot of planets actually existing quite close to their host star. So part of it observational bias, part of the way that planetary systems are built. The second question was about asteroid and Kuiper belts. You can actually already detect asteroid and Kuiper belts. So a lot of those coronagraphy techniques, maybe where you're just using a little piece of metal to block out the host star, are enough for you to see Kuiper belts, asteroid belts around other stars.
Those two methods you were talking about seem to be working best when we're in or close to the plane of the orbit of the planet. Now, what about when we're far off the plane of the orbit?
Right. So, so if you're on an orbit such that you're orbiting like this, so you're not transiting, but you're going like this, you're not going to get a very strong radial velocity signal, and obviously you're not going to see a transit. There are a method called astrometry that looks for, again, a wiggle in a star that would detect things that are on these types of orbits. And the Gaia mission actually might detect a lot of planets via the Gaia mission will probably detect planets using that method.
Right, and just, she talks about observational biases, so that when we discover an exoplanet, there are a lot of planets we don't discover. So a lot of our statistics of how many planets are out there are based not upon just the number we discover, but how many we haven't discovered because we wouldn't see them if they're in the wrong orbits.
Could you accomplish the same thing with your star shade as just putting a little black dot over the lens of the telescope? And if
So there's diffraction patterns to work out, and that lovely sunflower thing is actually optimally designed such that you don't get diffractive light into your telescope. So the circle creates an optical effect where you actually are putting a lot of your light back into your telescope, and the sunflower shape is the one sort of optimal shape that doesn't put that light back into your telescope.
Is there any theory that there's a connection with the planetary plane and the galaxy plane?
So I don't think there's a strong correlation between the planetary plane and the galactic plane. I'm not sure how much that has been looked at. Planets, if there's a multi-planet system, they tend to all be in the same plane. You do find planets in sort of weird orientations, but those tend to be more or less singleton or double planets. And that's usually indicative of what we call violent migration history. So basically, you have a Jupiter-sized planet that starts marching in towards its host star and starts chucking other planets out of the system, and that alters its orbit. The same thing could have happened in our own solar system if we didn't have Saturn, Uranus, and Neptune pulling back from Jupiter.
Okay, and there was a question online along that lines. Okay. They were talking about WASP-17b having a retrograde orbit compared to its star's rotation. Do we have a good explanation for the retrograde orbit of WASP-17b?
Right. So again, when you have these sort of violent migration scenarios, that can cause a lot of perturbances in both the inclination of the orbit and also the sort of direction of the orbit with respect to the rotation direction of the star. So you can get things in retrograde after they've migrated in. Yes.
there a new date for the James Webb to go up? And when it does, it'll be on the far side of the moon where it's much darker and it will never be able to be serviced and it'll...
Yes, I'm okay with it not being serviced. I have made my career on the Spitzer Space Telescope, which is in a Earth trailing orbit, not to be surfaced. The James Webb Space Telescope is now scheduled to launch in October 2018. So it'll be nice and far away from the Earth, lots of opportunity to observe. Mm-hmm.
Yes, in your plots for the transit spectra, when the planet goes behind the star, flux density decreases slightly. It's going to decrease when it's in front. Would you explain why that happens when it's in eclipse?
Yeah, so when you're actually looking at this system, you're looking at the combined light from the planet and the star. So all those photons that are coming into the telescope have a portion that's from the planet and a portion that's from the star. So when it's eclipsed, you lose the photons from the planets, and you can use that dip to measure the temperature.
Is the age range of the host stars sufficient enough that we're developing models of solar system evolution from these direct observations?
Yes. Many of these systems have ages that overlap the range of what we know of the age of our own solar system. Yes.
What methods are being utilized telescopically to search for extraterrestrial life, and can the government tell you not to disclose that information to the public?
So,
Repeat the question.
oh, sorry. Okay, the question is, what are the methodologies currently being used to spectroscopically look for extraterrestrial life, correct? And then,
Upcoming with James Webb.
upcoming with James Webb. And then the further question was if I'm not allowed to disclose that based on some sort of government secret rule. Second part is no, I can talk freely about it. There is the potential with James Webb to detect these biosignature gases in transmission for planets that are around late-type M dwarfs. So these are planets that are around particularly small stars. So if you have an Earth-sized planet that's around a star that's much smaller than the sun, you get a much deeper transit, and you're also able to get better precision in trying to measure the spectrum of those planets. So we may actually find O2 or signatures of disequilibrium chemistry processes in those atmospheres, but then we'll have to disentangle the whole thing of, well, it's around this cooler M dwarf planet or cooler M dwarf star, and what does that mean for the UV history and all of that sort of stuff for that planet.
The assumption, though, is that if you do that, you're looking at basically Earth-type life. You're not looking at other possibilities.
Right. And there are folks out there working. Sarah Seeger at MIT has done a lot of work looking at other potential biosignatures. So ammonia might actually be a biosignature in some cases. We aren't specifically looking for Earth analogs. We're looking for the chemistry and then understanding where that chemistry comes from. Because a lot of times if there's a disequilibrium process coming that you're seeing in the atmosphere, it could be abiotic or biotic.
Yeah, and if astronomer discovered it, it'd probably show up on AstroPH before anybody could tell anybody
well,
not
after
to.
the nature embargo.
After the nature embargo, right. Yeah.
There was a question of, yes.
I was wondering, what are the prospects of observing moons circling any of these through either Webb or HDST or?
Right. People have long searched for moons around these planets, and the way that they do that is actually looking for basically perturbations in the orbit of the planet itself. So again, much like in the RV method where you have this planet that's in the star orbiting around a mutual center of mass, if you have a planet and a moon, they have a mutual center of mass. And what will actually happen is you'll see slight shifts in the time of transit of the planet that is due to the presence of a moon. It's very, very small. So with Webb, we should be able to get down to the temporal precision. So you need time precision here, not spectroscopic precision, to be able to detect sort of, moons around Jupiter-sized planets.
These super, what do you call them, super Jupiter planets, necessarily gas giants? Could there be rocky planets that are,
So there's many Neptunes and super Earths, and then there's Jupiter planets. There are super Jupiters, I guess you would call them, but those are typically what we consider brown dwarfs. So as you go more massive than Jupiter, you go into this regime of these almost stars.
Failed stars.
Failed stars called brown dwarfs.
Haven't some people called Jupiter a failed star?
They have, but brown dwarfs are closer to failed stars.
So one of the questions that people were talking about, what is the definition of a super Earth in terms of how many masses, and where do you draw the line between a super Earth and a mini Neptune?
Right. So right now the definition of super Earth and mini Neptune is based on radius, because those definitions have been derived from the Kepler mission, which measures radii and not necessarily masses. So right now the breakpoint is that anything smaller than 1.25 Earth radii is a Earth. Anything between 1.25 and 2 Earth radii is a super Earth. And then you can go up to basically 4 Earth radii is a mini Neptune.
Okay.
Mini what?
Mini Neptune.
What is Neptune? So,
I mean, Neptune is a gas giant planet.
no, I mean, as far as relative to Earth.
So in terms of size?
4, 5, yes,
It's
size.
5 Earth radii. So
Five.
there was a.
What's the prospect of saying anything about the geology of the planets that you think?
That's a good question. It's actually quite good, because geological processes will shape what we see in the atmosphere. Okay, so geological processes shape what we see in our own atmosphere. We may see evidence of things like silicate weathering, interactions between the atmosphere and the surface that shape the sort of overall global weather patterns of those planets that we might be able to measure from phase curve observations. Perhaps one of the most interesting thing was the briefly mentioned lava planets. So those rocky planets that are really, really hot. Well, they're outgassing all sorts of stuff from their lava lakes that are indicative of what their rocky composition is. So that's one of the first places we'll start to look.
All right, any other questions? Yes.
One last question. Sorry. In terms of the level of precision for the James Webb, I understand that it's a much wider survey range. It's the whole sky, I believe. But
the test mission, or
the test mission. But in terms of the level of precision for how accurate the signal that it's reading, is that much greater than what we have now? The level of instrumentation, the accuracy, and would that have any impact on these methods for the RV method?
Okay. So the RV method has to be done with very high spectral resolution spectrographs that are only on the ground.
Okay.
We don't currently have, people have proposed RV missions in space. So RV is done from the ground due to certain limitations. Now with the TESS and the James Webb Space Telescope, so TESS will have a similar precision to its cousin Kepler, but it will do an all-sky survey around bright stars. With JWST, we'll actually have a much, much higher precision than we've had with HST, in part based on the wavelengths we're looking at. So we're looking at slightly longer wavelengths where there's just more favorable sort of ratios of the planet and star fluxes and that sort of thing. And the instruments in general are actually much quieter. So we can probably get down to something around 10 parts per million precision or lower. So some of these cases where for GJ1214b, where we had to do 12 transits to get to that precision, you could do it in 1 or 2 with James Webb. Mm-hmm.
I have another question.
Go ahead. Sure. There's somebody way up in the corner. I always like to try to choose people way in the back.
We hear about these stars that are far away with planets. Why don't we look at Alpha Centauri when it's so much closer?
Oh, we've been looking at Alpha Centauri like crazy, don't worry. So RV surveys have been pounding on that for a while and have gotten down to, well, there's definitely not a Jupiter there. It must be smaller and smaller. And the RV surveys will continue to sort of look for that. We have not seen any transits around Alpha Centauri.
I mean, and that's one of the key things that TESS is going to do by doing the brighter stars, the nearer stars. Kepler studied this one patch, but most of the stars that Kepler found are too far away for good follow-up. So the TESS mission will find the ones that are really good for follow-up with JWST.
Wow.
How was it determined what patch of sky Kepler was going to look at?
I don't know. They sat around and this.
Is that above your head?
Is Trump involved? I'm just teasing. I have to make some Trump comments.
If you were on another distant planet looking at Earth, we would be looking at it several hundred million years ago. From what we know of the history of Earth, could you have predicted back then that life would have evolved to the point where it is now?
Oh, God. Sorry.
So we probably wouldn't, we probably wouldn't see something that was so far away that would be the time span of several 100 million years. But there would be, of course, a time lag. And we've done a lot of studies looking at what's called Archean Earth. Because we could be looking at different stars that are at different ages, right? So we could be looking at stars that are younger than the sun or stars that are older than the sun, which if there's an Earth-sized planet around them, may be at different stages in their evolution. So they may be an Archean Earth or an Earth that's gone, past our phase and onto the older phase. So we've been able to study that, and we know what spectroscopically maybe an Archean Earth might look like.
Have you got any correlation on planet formation in relationship to star size? In other words, type O possibilities for planets going down the line in the western?
There are some trends with stellar type. There have also been trends with stellar metallicity, or the abundance of things other than hydrogen and helium. Small stars tend to form smaller planets. So you see a lot of sort of tight-packed terrestrial bodies around M dwarfs, and then as you go to larger stars, you are more able to form gas giant planets like Jupiter.
But I mean, the great thing is that we weren't sure that, around red dwarf stars, which are the most numerous type out there, that we could get planets, that there would be enough mass in the nebula that forms that star to form planets, but we see lots of them, which is great.
Mm-hmm.
Just want to comment. Excellent talk. So love it. I've seen multiple in the excellent talk.
All right, any last question?
There was one little hand down here, I think.
The little hand right up there.
The microscope we were talking about earlier that goes into space, do the scientists control it, control where it's going so it won't crash?
Yeah, so they're in fixed orbits, but the scientists who are going to command the Space Telescope where the point will actually be in this building right here with the James Webb Space Telescope. So the Mission Operations Center for James Webb is located on the other end of this building. So this will be the heart and soul of James Webb after launch in 2018.
James Webb will be orbiting at what is it called, Lagrangian point?
Yeah,
Will it be at the point or orbiting around?
Slightly orbiting around the point. Yeah.
Okay, it's approaching 9:30.
Okay.
Duncan is here. Duncan, raise your hand. All right, Duncan will take you across the street to see observing. Are they going to be able to see Saturn and Mars? Yes. They will be able to see Saturn and Mars. Next month, July 5th, Mr. or Ms. TBD will be talking. Let's give Nikole one more big hand. Congratulations.